This is how the Spacex Starship will land on Mars. Let's establish right now that we are not all rocket scientists or physicists. I'm definitely neither of those things, but luckily, we do not need to be geniuses to understand the basic principles behind interplanetary travel. So we're going to keep this all at a very accessible level. Before we can talk about landing on Mars, we need to know how the Starship got there in the first place. The thing that we always have to remember about space travel is that everything is always in motion, and within the context of a solar system, everything is moving in an orbit around the Sun. We are currently held in the gravity well of the Sun, and the only thing that prevents us from falling down any deeper is the orbital velocity of the Earth, which is approximately 30 kilometers per second. That's how fast we are traveling right now in a big circle around a star that takes 365 days to complete. The SpaceX Starship is currently humanity's best hope for setting foot on the planet Mars in your lifetime. The feature that makes the Starship so well suited for this job is, of course, its incredible power. There's no doubt that a future Starship will have more than enough muscle to send both crews and massive amounts of supplies on their path towards Mars. Going up is one thing, but what about coming back down on the Martian surface? We are talking about the most complicated maneuver of the entire journey, the make-or-break moment. And there's a lot more involved in figuring it out than you might think. Mars is further away from the Sun than the Earth, meaning that it isn't as far down into the gravity well as we are, and therefore Mars can travel at a slower orbital velocity without falling in. So Mars orbits the Sun at around 24 kilometers per second. Now, if we want to leave the Earth in a spaceship and explore the planets, we will become yet another object spinning around in the gravity well of the Sun. And just like the planet Earth, if we were to slow down our orbital velocity, we would start to fall into that gravity well. This will change our orbit in the direction of an inner planet like Venus. And by the same mechanics, if our spaceship starts moving faster than the planet Earth, we will raise the gravity well, bringing our orbit towards an outer planet like Mars. So traveling through the solar system is all about changing your velocity relative to your starting point. The technical term that we use to describe this is delta 5, where delta means change and V means velocity. We typically measure delta V in kilometers per second, so if the Earth is moving at 30 kilometers per second and you accelerate your spaceship to 31 kilometers per second, you have a delta V of 1. By the same measure, if you decelerate your spaceship relative to the Earth and travel at 29 kilometers per second, you also have a delta V of 1. And yet, if you blast off from the surface of the Earth at 1 kilometers per second, you are not going to begin rising up through the solar system. You aren't going to rise up above the Earth's surface because gravity and atmospheric drag are holding you down. These natural forces will affect the amount of delta V required to maneuver the spaceship. This is why it's so hard to get from the surface of the Earth to outer space. The delta V required to reach a typical low Earth orbit is going to be around 9.4 kilometers per second. That's a lot of acceleration, and that's why our Starship requires the massive power of the Super Heavy booster at launch. This is also why the Starship needs to stop for a refilling session in Earth orbit before it can continue on to Mars. Because we're going to need a lot more delta V to complete this journey. In order to change velocity, we need propulsion, and propulsion needs fuel. The advantage of filling up in orbit is that it resets our starting point. From here, we only need another 9.5 kilometers per second of delta to V to reach the surface of Mars. So basically equal to the change required just to escape the Earth's atmosphere. But there is going to be a big difference in the approach we take for the next leg of the journey, because while escaping the Earth was all about speeding up, landing on Mars is going to require a lot of slowing down, and this can be just as difficult to achieve. A fully fueled starship in low Earth orbit is imagined to have enough thrust for somewhat between 6 and 7 kilometers per second of delta 5. This obviously is a bit short of our 9.5 kilometers per second necessary to reach Mars, but that's okay, because the same forces that made it so difficult to escape Earth's atmosphere, gravity and aerodynamic drag, are going to work to our advantage when we come in for a landing, effectively increasing the delta V potential of our starship. So here's how it's going to go down. We are in orbit around the Earth, but even a few hundred kilometers above the surface, we are still firmly caught in the Earth's gravity wall. The only thing keeping us up right now is velocity. If the starship were to slow down at all, it would start falling back towards the Earth. By that same reasoning, if we do the opposite and speed up, then we will continue to rise up into space. Because we are still so close to the Earth, we need a lot of delta phi to fight against gravity. The ship will have to accelerate by 2.44 kilometers per second just to reach a height of geostationary orbit. Another 0.68 gets us to the height of the Moon. Up here, we are finally on the edge of the Earth's gravity well. The force of gravity is infinite, but the power of attraction dissipates relatively quickly as you move further away. Now all we need is another 0.9 kilometers per second of velocity to escape the Earth's influence completely. From this point, floating in the vacuum of space far beyond the Moon, we only require 0.39 meters per second of delta 5 to achieve our Earth to Mars transfer velocity. This second leg of the journey has used up 3.6 kilometers per second of delta 5, which is at least half of the potential energy in our starship, if not more, and that means that we do not have enough fuel left to successfully land on Mars with engines alone. And here comes the problem that we need to solve. All of the velocity that we acquired to escape Earth's atmosphere and gravity well has got us traveling around the Sun at a significantly higher speed than the planet Earth, which was already traveling at 30 kilometers per second to begin with. The planet Mars, on the other hand, is orbiting at a speed of just 24 kilometers per second, so we are moving significantly faster than our target planet, which means that we are going to overshoot the planet Mars and end up stuck somewhere in the asteroid belt unless we start slowing down. After several months of coasting through the vacuum of space, we need to execute our first deceleration burn. After flipping the Starship around and getting the Raptor engines back up to speed, we have to shave off 0.67 kilometers per second of velocity in order to become captured in the gravity well of Mars. So friends, what do you think about this? Write down your views in the comment section. If you liked the video, then like and share it with your friends and space enthusiasts. And don't forget to subscribe to our channel to get interesting videos.